the stuff. We're doing 1D, 2D, and 3. No, okay, 1D cylindrical integration and 2D spherical integration, and those things were not matching, which is a bit concerning. So I want to what I probably want to do is I want to try a simple example, and this is the cylindrical integration. I think there's the example of the one radius 1 sphere. Exactly, the volume of a sphere. And I think I can, because that's simple enough, because it's just 1, right? I mean, the thing is, the function here is always expressed with a radius, which is 1, right? No matter what point, no matter what, is it though? I think so, right? The unit disk. Don't forget to include the R. We're doing cylindrical? Oh, this is cylindrical. I want spherical. From Khan Academy. And so it's kind of the same idea, right? So, but it's yeah, you have these basically we're building up to. When you're triple integrated, choose to describe function in the bounds of your region using spherical coordinates. The tiny volume dV should expand as follows. Okay, we skip the explanation. We want to go through the example of the sphere. So okay, so that's just really the way this is, right? We can start setting up our integral like this. 0 to r, 0 to pi, 0 to 2 pi. Oh, that's interesting. Why pi? Okay, that starts getting interesting. Because I thought it's a sphere, so you'd go 2 pi from both angles, right? Let's go again, as I said, I'm going to skip this because that's just a derivation of how to expand the volume, sort of the dV, right? You cannot just represent it with you must also remember the R, exactly. So volume of a sphere revisited. This might be the simplest possible starting example for triple integration in spherical coordinates, but it lets us compute an interesting non-trivial fact: the volume of a sphere. What is the volume of a sphere with radius R? Situate the sphere such that its center is on the origin. Cool. If we were doing the integral in Cartesian coordinates, we would have to, it's super ugly but common situation where the bounds of inner integrals are functions of outer variables, blah, blah, blah. But if we kind of set up the R, the phi, and the theta, accurately describes all the points inside the sphere of radius R without running over the entire sphere multiple times. Okay, so now we have to choose the boundaries. Okay, let's check again these, right? So of course it's just pi. Of course it's just pi, because this angle kind of just travels pi, because then the theta travels 2 pi, and so you're wrapping if you think about like the 3D version of these, you're kind of giving it a wrap. So it's like you're rotating this thing all the way like 180 degrees, and then with theta you're doing the 360 degrees, so you cover everything, and then with R you go from the center to the top, to the sort of to the edge. So okay, Okay. Okay, so I would say that r goes, yeah, so I would say that's wrong. Then, you know, but essentially you could also do it the other way around. It doesn't matter which one. Does it matter which one you, I think it doesn't matter, right? Because if you say I'm gonna do the full round, I'm gonna do the full round, and then you just do basically, yeah, you can just do with theta, you can do pi, like pi, and then you know, and then you do pi with that doesn't, I think it doesn't really matter, but let's stick to these. So I think it's definitely B. Yeah. And then so we use these thing here, and so let's try to set these up here, and let's see if it works. Let's just comment all these things, and let's have an example. First of all, let's use NAR, and then let's use like B is for like, I will just call theta. Okay, so what is theta? So theta is this guy, and what is phi? I'm not so sure if this is this, but let's call it phi. I don't know if this is phi. I think it's phi. Let's go theta and phi. So we're not messing up with stuff. So this is TH and PH, or we'll just call it theta and phi as well. So makes it easier. Phi. Okay. Cool. So let's do an example where so this is the basically radius r as a check, because that's the simple thing. So it's really, you know, it's just really that expression, right? So with I'd say the function is just it's a constant, really. No, is it? Yeah, well, let's, you know, interesting, right? How do you frame, I mean, it's really, it's just the integral of the ball of this volume, and so we're literally saying this is how you expand the volume, and really you just define that R in here, right? But then the there's no really a function that you're integrating inside, is there? I don't think there is. It's just your, yeah. That is what's that's currently what's bothering me conceptually. I think I can set this to 1, but I'm thinking, why would that be 1? Because the function, oh god, because why would it be 1? I mean, why would it be 1? Why would it be 1? I mean, if this is what we have, right, and we think of what will be the function of the sphere, is like you give it an x and y, and then this function basically sphere equation, right? I mean, you have that equation, so why aren't we why aren't we using the equation of a sphere as a starting point? That's a good question. Well, in a way, you're doing that already, because this is r is basically r squared, is it? The sphere with center, so this is the center. If you give like, yeah, you can express, you know, you can express these by just the square value of the radius. No. I don't know if you know what I'm saying. Like I'm you know, you can generalize about these by saying like we have a function and we're going to do an integration on and of this region in spherical coordinates. Okay, but sort of as a reference, it just intuitively makes sense. It's just the volume. That is the volume. That is what you want to do. So essentially, that's kind of what you've defined in here by definition. It's you know. So when you're performing a triple integral, if you choose to describe the function and the bounds of your region using spherical coordinates, the tiny volume dv should expand as follows. But I don't quite get how you translate the edge case here of like the sphere. I get it, like you derive that by working on the spherical chunk. So constants are so essentially that is that is what you're doing. But then I'm not so sure why. I'm not so sure why then this works as a general expression, but let's keep that aside. Let's just think of these as that's the base case. The base case is basically you don't have any function. What you're doing is the volume of a sphere, and you know, here you work out the concept of that is the function in a way for the sphere. That is the function. It's just that then there's this kind of concept of if you multiply by another function, then you're getting the integral of the volume of that function within the spherical bounds, so to say. That is something that is not so clear to me though. Why would the multiplication do the trick here? But okay, so let's just you know, let's just do these like that. R squared sinus theta. So we have, okay, so so basically there's no you know, no kind of real function. So I mean, I just kind of say S1. I'll just start with the S1 as integrate. I mean, you know, in a way, S0 is kind of the is this thing, right? It's R squared sinus of phi, right? That is what we're doing here, is it? Spherical coordinates, sorry, here. R squared sine phi, and then we do, yeah, and then, exactly, yeah. That's what it is. And then S1 is like integrate S0 first. So cons none. So first what we do is we do R, and then R is between 0 and you know, say n, right, the radius. Let's just n for the radius, or let's just put a number just so we can compare. So let's say radius 5. And so this is the first thing, and then we do S2 equals integrate S1, and we do then what do we do then? We do phi. So first we do the one that's pi. That makes sense. And I think that's what I'm doing here wrong. Yeah, I think that's what I'm doing here wrong. Now I'm realizing I think one is like pi divided by 4, really. Because I was doing pi and then I'm counting things twice, of course. Of course. Okay, that actually helped, you know? You see? That actually helps. So that's phi. And we do 0 to pi. And we do the same, conditions none. I think I know then what I've done wrong, but let me just finish the example, okay? And so S3 is basically, so what we're doing here is basically saying, here we're doing theta. Here we're doing theta, and theta is like, and we know it's 2 pi. Because we do first pi, and then we do like, you know, like just to think about it, it probably makes no sense, but like you, maybe it's because it's obvious in my head, but it's probably not. Just so you first kind of do the pi, so you first do the pi, so you kind of cover all this area, right? If you think about these are the coordinates, and then we do the 2 pi. We brush, like we comb, or you know, we do the 2 pi here, so that's 2 pi, and that, like, you know, that here is just pi. So we don't kind of walk through the same area or space twice. That's important, and I think that's what I was doing wrong in my example, because I know that it's kind of something like this, right? And I was doing 2 pi, which is okay, but then I was doing pi like that, which makes no sense, because to be honest, I just have to do pi halves, because I just need to do cover this angle, right? Because then with the 2 pi, I'm gonna already cover all the rest of the area, right? I think that is how the boundaries here were badly defined in my example. I think that's the mistake that I was making, at least. Let's see. So, yeah. So, you know, actually, let's keep these to like R. Let's just define for the example like a symbol R, which is basically, we know that it's real, and we know that it's also positive. I want to compare it to that example. So, okay, I think it makes sense. Well, 1, and then here we integrate 2. And so now I can just print S3 and see what happens. Python x21a. Okay, so I get this thing here, which is 4/3 times pi r cubed. Yeah, that's cool. Matched it. That's awesome. So this is work. This is spherical coordinates, and now we want to do cylindrical coordinates. And essentially with cylindrical coordinates, it's kind of a bit of the same, right? Cylindrical coordinates. So, but here we just have r and then theta and r and then z, right? And we know z kind of goes from r and theta should be used to get this unit disk. Yeah, definitely 0 to 1. It's definitely A. Cool. And then Z. Okay, that's the interesting part, because that's maybe what I'm getting wrong as well. So for a given value of r, which are the following. I mean, Z is minus. It's not minus r really. Oh yeah. No. Yeah, minus r. No. Why? It's one of these things, I think. That's the problem. I think that's where I was also failing. It's one of these. I'm sure it's one of these. Why? Because given a value of r, the z boundaries are like, yeah, you kind of have to calculate, you know, the z values are different given a specific r. That's a good point. That's definitely a good point. I think that's the mistake I was making, because you can't just fix the z to be between 0 and 1. That's not how this works. You have to define for a given small r what are the z boundaries, right? Which is for r0, it's your radius 0, it's 1 and minus 1. For r1, then z equals z. Right? There's no boundary, but for r somewhere here in between, we need to calculate these things here. Let's figure out how to do that now. But okay, so let's first set these up like these. So okay, so we know it's like that. So that is y 0 to 1, right? Yeah, 0, yeah, exactly. 0 to, well, 0 to r it would be in this case, right? Volume of a sphere. They could have done. Oh, I've seen the solution. But they could have done. Let's try to see if we just put r, because I think then the r goes here, right? So if we do r and then we say, well, that is just the way this is derived is these being just r. So this is just r. That's kind of the baseline, and then we are integrating on. First, we're integrating on z. First, we're integrating on z, and that doesn't have to be positive. That's wrong. Okay, maybe for my example that's not wrong. That's correct. But let's see. For this example, we define z as being just a real number. And so the first integration is z, but we still don't know these bounds. We still don't know these bounds. Then we have then what do we have? Then we have, there's that. Then we have r. Why are we doing this? Does this make sense? Cylindrical. So we're doing first the integration over z, then we're doing the integration. So first we're doing the integration over z, then we're visually that's confusing. Then we're doing over r. I'll have to double check that. 0. So this is definitely 0, 0 r, right? And this is r. And then we're doing theta, and theta is just 2 pi. 0 to 2 pi, that makes sense. But then what are these boundaries, right? So I kind of, I mean, now I kind of know that they are these, but so let me just put them and then see what happens. At least see if we can verify these. So -1, so it's minus square root of, okay, so minus square root of, my guess is r minus r squared, right? And then the same thing, positive. I think that's my guess. See if we get the same things now at least. No. No. Well, what if we just stick to 1? Stick to 1, and then kind of let's stick to 1 here as well. See if we at least get the same here. Yeah, okay, cool, that makes sense. But then it's like these bounds are, then it's different. Then this is not just r. If I want to make these r, but let's try to. Okay, but it's the same. I don't want to lose. I know I could probably, and I'm like almost. I'm so tempted to just try to generalize that to r. But I'm also tempted to just kind of fix my issue and then check whether the stuff is correct below. Cool. Now, because I think the trick here is going to be the following. So now I have this shit. Right? And so I think the easiest is to use cylindrical coordinates in this case, because it's got a z symmetry. Right? It's got this symmetry here. But then that's going to be an interesting one to. This is something that, so these guys here, okay, so this is derived like the distance from a point r theta z to the origin is these. So, okay, yeah, and then so you define them like that. Yeah, so z is plus minus these. Okay. Okay. How do we do this? Now that's going to be the trick. So this is all nice and it worked well, and we compared and they are the same, and that makes total sense. So this is the example. And now let's take these variables. So this is the example test, and now the exercise. So we have n, we have a, which is real, we have r, which is real and positive, and we have theta and phi, and then we have z. And so our let's kind of, yeah, let's do what we so our function to integrate is this one, and so what we're trying to do here and I think I'm gonna skip. I think I'm gonna skip then whatever all these different spaces, and I'm just gonna stick to the case at hand that I know we're talking 3D space. I know it's got this shape. I guess so. I guess we're talking 3D space. I mean, this is still another challenge, right? I guess it's 2D space, right? In terms of the X and Y, and then you have like a 3D setup because the Z is a 3D. So I think this is what we should stick to, definitely. At least this is what we know how to work. Although again, yes, I know that this is the one. You know, you can work out that like generalization. I think that was the generalization I was trying to work out. But let's see if that, if put this way, works well. So function to integrate. So we have the function to integrate, and then we're putting the ends at the n at the end, and we're defining S0, and we're using cylindrical stuff, right? Cylindrical coordinates method, cylindrical coordinates, and so we're basically the S0, so the setup is the same. The S0 is just R. That's the radius of our example. It's the radius of our setup. And then S1 is our expression. So it's our function that we're integrating, right? With the ends out of the integral, and kind of we bring it back at the end. So this is S1. Exactly. It's our starting thing, right? So what we do though now is the following. So we start with S2, and we say, and we follow the same pattern like here. So first we integrate on given a Z, what are the boundaries? What are the R's, right? And that's the trickiest one. That's the trickiest one. You know what? Maybe I'll just copy these. Yeah. So I'll just copy these. The solving, that's definitely something specific for later. So I'm going to copy these. I'm going to say, well, we do S1 times S0. That's kind of the main difference here, because we have that basis, but then here we have an F, and a function, right? So we'll just override it. It's fine. Or S, we'll call it like S01. S01 and S02. S0. That's just nasty. S01, S02, S01. So we'll do S01 times S02. Sorry for the confusion here. And so we're doing Z, and then these things are definitely unknown. This is to do. So find boundaries. That's going to be the complicated exercise. S2, then we're integrating on the radius. Now the radius, we know that it goes from 0 to infinite. Opa. This we know for sure. The radius can go, 0 to infinite. And theta, we know that it goes to pi. So that's the easy one. So now the question is, how do we find these boundaries? How to find Z? Or I'm also thinking, like, wouldn't it be easier to just use spherical coordinates? Because The radius, we know the radius boundary. I mean, what if we used so, because it's going to be a faster example, which I'm assuming I'm not so sure if it's going to work out, but I have the feeling it's easier to set up. I have the feeling, okay? So here S0 is these. S02, and this is S01. So no, this is S02. So here we do S01 times S02, correct? S01 is still our expression. S02 is this funky thing here. And though now we do the radius, which we know is 0 to infinite, and then S2, and so S2 is phi, and here, as I said, here we go from 0 to pi divided by 2, because remember we just go like these, and then we do the whole round, and then we do 2 pi with theta. And so we have S3, right? And then we do S3 times these, and we solve for n, and so we print S4. Does this make sense? This seems an easy setup, but it doesn't, I don't know, I don't think it's gonna work. Because I have the feeling I have the feeling I don't understand how that bounding really works, whether that bounding it with a sphere like these makes any sense at all. Let's just try at least. Let's see if it works, and then we'll leave it here today. It also doesn't work fully, huh? No, that's not exactly that's definitely not the answer. That's what I thought. That's definitely not the answer. I mean, because we're just doing this, like, that's the problem. This is 2 to the power of like 1/2, and then 8 to the power of like 3/2, 3 divided by 2. That's definitely not the solution. That's definitely not the solution. But okay, at least we've tested stuff, and I have the feeling this is going to be the one, this is going to be what works out. But then I don't know exactly why this doesn't work out. Like, so if it's spherical coordinates, which seem easier, then why can't, like, why can't you, then I guess we would have to rewrite these properly, because I don't understand. So how is it that you're like, this is an example of what, of like region of the first octant. So this is just probably an easier example. Oh no, it's like this. But it's different, because this is, it gives you the region, and then express the region in spherical coordinates. We get that this is the function, and then we compute the integral. So yeah, basically, I don't know, I'm missing something here, but I think I'm almost there. I have almost a feeling like this is gonna work out if I find the right boundaries, or how is like given a specific R, what are the Z boundaries, right? And here, remember, if this is what we're doing, it's like given a specific R that I know that we know the Z of, like the boundaries are like 0. Yeah, well, given a specific radius, yeah, but I have to calculate inside as well, right? That's what's tricky, because I have to express for for every sort of point inside the volume, like what it's an expression of the boundary of Z. In a way, I think it's not like that, because then it's going to have a value here and then a value, I mean, I think the bottom is always going to be 0. That makes it easier. Yeah, I think the bottom is always going to be 0, but then the top is what's kind of complicated. So this is definitely not 1, which is what I was doing before. It's a more complicated expression, which I have to kind of calculate as well. Cool, let's see. Good enough. There is definitely some progress in there. It's just maybe because I'm not like fully understanding the concept of doing it, like the importance of these boundings, and I don't really quite understand why then why then generalizing things like these just work. Like, I guess this is important, and maybe I just have to finding the boundaries is important. Where are Z's going, kind of, because it's an approximation. If I just kind of say, oh, I just go from 0 to 1, that's the mistake I was making. If it's like 0 to 1, then it's gonna make it like it's not gonna do that properly. It's got to be a function of R, right? So I think the boundaries are actually super important. Anyway, good session. See you next time.